Hi, pre-calc students. This is Unit 8, Day 1, and today we're going to start learning about an introduction into some trig needed to talk about complex numbers in this unit. So these are notes in your packet if you want to take those out and start filling them in. Today is really purely review from some of the trig that you would have learned in Algebra 2 last year. So first thing that would be good to start with would be the definition of a radian. So an angle measure of 1 radian occurs when the radius of a circle is equal to the measure of the intercepted arc. And you can see that I've drawn this picture over here where I've tried to draw it such that the measure of this arc right here that's being intercepted is the same length as this radius. That's the intention. And when that happens, the angle theta, that's the central angle right here, theta would equal 1 radian under those conditions. So now that we kind of have that established, that is the definition of a radian, the most common radian equivalent that students typically remember is that if you have pi radians, that is equivalent to 180 degrees. So if you were to take this same distance and kind of like wrap it around again, 2 radians would be somewhere in the second quadrant, 3 radians would be like just barely halfway around. And that extra distance would get you to pi, because again, pi is about 3.14. So half of a circle is either considered to be pi radians or 180 degrees. This unit will focus on both, so you'll need to know both radians and degrees throughout. So it's good to just have a good familiar background with, first of all, given these degrees, what would their radian equivalencies be? Let's start actually down kind of towards the end of the chart, because we already discussed 180 degrees is pi radians, so we can fill that in. And maybe if I work backwards from there, 90 is half of 180, so then this would have to be pi over 2. 60 would be a third of 180, so that's pi over 3. 45 is 180 divided by 4, so that's pi over 4. And finally, 30 degrees is going to be pi over 6. So these are ones that probably look familiar, again, from last year, because you use those a lot when you do trigonometry in Algebra 2. Working forwards from here, these two also come up pretty frequently. 270 is going to be equal to 3 pi over 2, 3 halves pi. And then the last one, if I double 180 to get to 360, 360 would be equivalent to 2 pi. So these are ones that, again, as they come up, I'd want you to almost in your brain automatically know that pi over 3 and 60 go together, and so on and so forth. But if it's not something that's a common one in this list up above, there are ways in which we convert between degrees and radians. And as it turns out, if I come back up here, if I were to divide both sides by 180, we would get that pi over 180 radians is equal to every 1 degree. And that happens to be our conversion, that if I have a certain number of degrees, if I say I have x degrees, I can multiply that by pi over 180 in order to convert that into radians. So for example, if I gave you 120 degrees, which is not in the chart up above, 120 can be multiplied by pi over 180, and the radian equivalent of 120 degrees is either 120 pi over 180. You want to just write it like that. But the nicer form of this is just reducing that, so this would actually reduce nicely to 2 pi over 3. Eventually, you'll start making some connections too, like, oh, 60 was pi over 3. 120 is double 60, so then that's why we get double pi over 3 in this case. If I wanted to go in the reverse direction and have what 1 radian is, you would just take 180 and divide by pi. So if you have a certain number of radians, multiplying by 180 over pi is the conversion in the other direction. So for example, if I gave you 5 pi over 4 in radians, multiplying by 180 over pi would convert it to degrees. What will oftentimes happen, but not always, is that a lot of times radian angles have pi in them. So if you see that the pi's will cancel nicely, you can do 5 times 180 on your calculator and then divide by 4. That winds up coming to 225. The other way to do this is just simplify a little bit further by saying 4 goes into 180 45 times. 45 times 5 is that same result, 225 degrees. So if we're feeling pretty good about remembering what we got with degrees and radians there, let's move on to the 6 basic trig functions. SOHCAHTOA is kind of a good phrase that I think a lot of teachers use to help remember the patterns for some of those trig functions. What I want you to do in the triangle below is label that angle theta, and then I'm going to call the horizontal distance x at the bottom, the height of this right triangle y, and I'll call the length of the hypotenuse r. R will eventually become known in this unit as a radius length, which is why I'm choosing R specifically for the length of that hypotenuse. So if I were to talk about the 6 basic trig functions, 3 of them are coming from SOHCAHTOA. So when I say SOHCAHTOA, we're talking about sine, cosine, and tangent. And what we'll do is we'll list the ratios for each one in general, and then I'll apply it to the specific triangle. The ratio for sine in general is opposite over hypotenuse. So that's where O and H come into play. So the opposite of angle theta is the y, and the hypotenuse is the length r. So in this specific triangle, the sine of angle theta would be the ratio y over r. If we move on to CA, adjacent over hypotenuse is what we have for cosine. The adjacent side to angle theta is the one that's right next to it. Down below it, it's the side labeled x. Hypotenuse is still r. Finally, tan is known as opposite over adjacent. So therefore, opposite is the y, the adjacent is the x. Tan is the ratio y over x. And although these are kind of the 3 main functions, we have 6 total because then we have 3 functions that represent the reciprocals of each of these. So the reciprocal functions are cosecant, secant, and cotangent. Perhaps those names sound familiar from last year, but if not, cosecant just winds up being the reciprocal of sine. So instead of doing opposite over hypotenuse, you would just do hypotenuse over opposite. This would be the ratio r over y. Secant, we would flip over cosine. It would be hypotenuse over adjacent, which is r over x. Cotangent's the reciprocal of tangent. So if I do adjacent over opposite, that total is y over x for the ratio. So in this unit, although it's good to know all these because eventually unit 9 has all 6 of these pretty frequently intermixed, the main focus will be the left side for unit 8. We're not going to see a lot with the reciprocals, if at all, beyond this when we get to our next part of unit 8 here. So if you go to the next page in the packet, at the top we have something called the unit circle, and this might look familiar from last year. The unit circle is a circle with a radius of 1. So you can label some things on the unit circle, like for example, the coordinates of these points are going to be of importance to us. So if you go right 1, up 1, left 1, or down 1, these would be the coordinates, given that this circle has a radius of 1. The other thing that will be of importance to us on the unit circle are the degree measures at each of those locations. So when we sketch angles, 0 degrees is up here. When I say up here, I actually mean to the right. And then as I rotate counterclockwise from there, 90 degrees is at the top of the unit circle. 180 is halfway around. 270 is at the bottom. And then if you go full circle, 0 and 360 correspond with the same location. So if you have your unit circle labeled the same way that I do here, I'm going to draw this triangle in. And when I draw that triangle in here, we're going to drop that height from any random point on the outside of the unit circle. So if you've drawn a triangle in the first quadrant there, label that point where it hits the circle as x comma y. And what you can then do is go in here and label that this is x and this is y. Because to get to the point xy, we have to go right x and up y. I actually know that this length is 1 because it's a radius drawn in the unit circle. So every radius length has a length of 1, whether it's diagonal, straight up, straight across. That length is 1. And the final thing I need you to do in this picture is put a theta in as that angle that's connected to the origin there. So that central angle from the x and y axis there, we're going to label that as theta. And then what I'll remind you of is that the unit circle has some nice correspondence based on this picture with sine and cosine specifically. So for example, what I mean by that is if we evaluate sine of theta right now, sine of theta would be opposite over hypotenuse, which is y over 1. So very simply stated, sine theta is the y value of the corresponding point on the unit circle, which means that if I said, what's sine of 90 degrees, which is up here, sine of 90 corresponds with the y coordinate of this point on the unit circle. Sine of 90 would be 1. We'll fill that in the table below in a second. Okay, moving on to cosine of theta. Cosine of theta would be adjacent over hypotenuse x over 1. So cosine theta is the x value of all those coordinates on the unit circle, which means that every point on the unit circle, x comma y, corresponds with cosine of that angle theta and sine of that angle theta. That is a conclusion that I believe you've seen last year in Algebra 2. But if you don't remember it, that's why we're here now, reminding you of that. Lastly, how would you do tangent given these special angles on the unit circle? Tan of theta would be y over x, right? Opposite over adjacent. So the y value divided by the x value, notice how that's the same ratio as dividing sine over cos. And that will be a pretty big concept heading into Unit 9 beyond this. We're going to definitely be working with the fact that tan is sine over cos very frequently in that unit coming up next. So today, not only is it a good building day for Unit 8, but definitely for what we do in Unit 9. I'm going to fill in this chart pretty quickly because at this point, I'm just going to use the unit circle values and know that sine is y, cosine's x, and tan is y over x to be able to fill in these rows based on the coordinates of the points on the outside. So what I'm going to do is I'm going to start at 0, and for sine, check out all the y values at those locations. Sine of 0 is 0, y coordinate. Sine of 90 is 1. Sine of 180 is back to 0. Sine of 270 is -1, and then 360, these two columns should always be the same because 0 and 360 are in the same place. If I move on to cosine, cosine of the angle theta corresponds with the x value of all those locations. So cosine of 0 is 1, cosine of 90 is 0, keep going all the way around here, -1 at 180, 0 at 270, and finally back up to 1 by the time we get to 360. And finally, for our last ratio for tangent here, tangent is going to be y divided by x. So you can actually just not even look at the unit circle. You can take your answers and do the top divided by the bottom number. 0 divided by 1 is 0. 1 divided by 0, however, is no good. That's undefined. Won't be a big deal in this unit. Will be a bigger deal heading into the next unit, Unit 9. So 0 divided by -1 is 0, but when I flip it, -1 over 0 is also undefined. And at the end, 0 over 1 is back to 0. So tangent has some stranger scenarios there, especially with those undefined values. We'll see how that plays out later on in our course. What I want to do is, now that we've really developed the concept of the unit circle, remind you of some patterns associated with special right triangles. So the special right triangles that I'm talking about are the 30, 60, 90 triangles. And the other one is the 45, 45, 90. And these are special triangles because the ratios of the sides are always in a really nice proportion with one another. So in general, in a 30-degree triangle, across from the 30, we would label that as x. And what happens is, whatever's across from 30, the hypotenuse of this triangle is always double that. So that would be 2x. And then across from 60 is that number times radical 3. So whatever's across from 30, across from 60 is that number radical 3. And then the hypotenuse is double that. I go over to the 45-45 triangle. This is actually an isosceles triangle. These legs would be the same because those angles across are the same. So the ratio here is that if I call both of those x, that the hypotenuse is x radical 2. Again, patterns that you've seen before, so I hope that these don't look too foreign to you. The simplest case for us to consider is when x equals 1, by the way. That's the smallest positive integer we can pick for x. So if x is 1, this side would just be radical 3, and the hypotenuse would just be 2. That will give us the most reduced answers when I evaluate down below. Same thing over here. If x is 1, then the hypotenuse is 1 radical 2 over there. And these are the values I'm going to use when I go ahead and simplify something like cosine of 30. So to evaluate some of these, cosine of 30, for example, would be the adjacent over the hypotenuse from the angle 30 degrees. Adjacent's the radical 3. Hypotenuse is the length of 2. Cos 30 is radical 3 over 2. These are really special and important values that will tend to come up over and over and over again. Moving on to sine of 45. Let's jump to this triangle with a 45-degree angle. Sine would be opposite over hypotenuse. So sine of 45 would be 1 over radical 2. Typically what we do from there is we rationalize. We don't leave radicals in the bottom usually. So if you multiply by radical 2 over radical 2, might look like a familiar step to you. The top of that becomes radical 2. And the bottom, radical 2 times radical 2, is actually just 2. So radical 2 over 2 would be the answer for the evaluating of sine of 45. If we do tan of 60, coming up to this angle up here, we're going to do opposite over adjacent. The opposite to 60 is the radical 3. The adjacent's the 1. So radical 3 over 1 can just simply be written as radical 3. And once you have that row all set, filling in the rest of the ratios, just choosing, it's still 45, 30, and 60, but just different functions there. I bet you can probably try these pretty quickly. And then go ahead and we'll go over those next time we're together in class. So I'll leave those blank for now. On the last page though, last thing we should talk about today is just some quick rules for evaluating trig functions at different angles that are not 30, 45, and 60, or even the ones that we talked about earlier, which were the 90, 180, and 270. So the rules are pretty simple, and this is something that you did last year for sure. Sketch the angle, make a right triangle with the x-axis, find the reference angle, label the sides, and evaluate. Those are the 4 steps we're going to follow. So I'll show you what I mean by that. So for something like sine of 210, first thing I would do is I would figure out that 210 is in quadrant 3, right? Because it appears 0, 90, 180, 270, full circle is 360. I won't do that every time, but just for this first one. 210, when I start at 0, would rotate counterclockwise and wind up stopping in quadrant 3 like that. So when you sketch where the angle ends, the next thing I do is I draw a line back up to the x-axis. So I've already done steps 1 and 2. I sketched the angle, and then I made a right triangle with the x-axis. The next thing it says to do is find the reference angle. And what I mean by reference angle is, what is this angle on the inside here? And when you're in quadrant 3, I know that halfway is 180. So if I take the full circle of 210, and I subtract 180 right here, that's going to leave me with 30 degrees as the reference. The reference for most of these should be something like 30, 45, or 60. All right, so if that's 30, that makes this 60 down here. And if I label the sides in a 30, 60, 90, you might have to flip back a page to remind yourself of the ratio. Across from 30 is 1. Across from 60 would be 1 radical 3. And the hypotenuse is 2. Okay, so if you have all those things labeled, the next thing you're going to do is think about that when you're at a point in quadrant 3, the way you got there is you went left and down. Left and down are both negative directions. So I'd like you to put negatives on those 2 sides. I know they're lengths in a triangle, which seems weird, but it will help you to get the right answer. Because in the last step here, sine is going to be opposite over hypotenuse. So the evaluate part from this reference angle would be opposite is -1, hypotenuse is 2. So the final answer is a ratio of -1/2. And I understand just seeing 1 could be a little overwhelming, even though it's something we've seen before. So my intention is to let's just do 2 more in this video, and then we'll try the rest in class next time we're together. Cosine 150, we'll jump to that one. So cosine of 150 would be, if I sketch the angle, not quite halfway, because halfway is 180. So this angle will stop in quadrant 2. Draw a line that ends the angle, and then connect it down to the x-axis. So there's your picture to start cos of 150. Next thing we have to do is then find the reference angle, which is this little piece in here. If I've gone 150 up to this point, we need another 30, again, would be the reference angle, to complete half a circle. Sometimes I just do that by doing 180 minus the angle 150 to get the reference on the inside. So we have again a 30, 60, 90. Across from 30 is 1. Across from 60 is radical 3. Hypotenuse is 2. Same labels that I was using earlier. But the last thing we have to consider is, do I need any negatives on the legs? Hypotenuse, by the way, is always positive, just for pattern purposes. But to get to this point, I went left and then up. Well, left is a negative direction. Up, we would leave positive, right? These are positive y values when I head up. So to get cosine, which is adjacent over hypotenuse, adjacent to this is the negative radical 3, and the hypotenuse is 2. So the final answer would be negative radical 3 over 2. Last but not least, we'll do one with tangent, and we'll address what's going on with this weird negative angle at the end here. So tan of negative 135 would rotate around in a clockwise direction instead of a counterclockwise direction. That's the only big difference when we have negative angles on the inside. So negative 135 is going to come around this way. If you think about halfway being 180 still, negative 135 will stop in quadrant 3. Okay. So now that I have my picture, once I stop the angle, connect it back to the x-axis. The reference angle this time, the way we would calculate it is, again, halfway is 180. 180 minus that 135, this case leaves you with 45 in this spot. So luckily we have another special triangle of 45, 45, 90. The way we label the sides in this triangle is we go 1, 1, radical 2. And if these patterns aren't as readily available as you'd like them to be right now, this is primarily the whole unit is using these special triangles. So we will definitely get a lot more practice by the time we're finished with Unit 8. So to get to this point, we went left and down, so that's -1 and -1 for the legs. And then finally, lastly, from this reference angle of 45 up here, tan is opposite over adjacent. So if we do -1 divided by another -1, that result is a +1. There is a pattern that you may recall from last year for the signs of these trig functions in the quadrants. So in quadrant 1, we usually put an A, and then in quadrant 2, an S, a T, and a C. I'll see if you remember what that pattern is next time we're in class together. But that pattern might sound familiar to you. Maybe there was even a phrase your teacher used last year to help you remember that. We'll talk about that pattern a little bit more tomorrow. So hopefully you got a little bit more of a trig review from some of the things that you've seen in the past. If you have any questions, we'll talk about them next time we're together. Have a great rest of your day.